Let's continue with our lecture. Today we are going to talk about the Fourier series as a part of Hilbert space or the linear vector space. This is a part of mathematical method course PH 3103 at ISAR Calcutta. Let's more carefully look at the eigenvalue problem in Hilbert space. So we have seen that d square by dx square is one of the promising differential operator to look at the eigenvalue problem. Let us look at it more carefully. Let's take an interval, closed interval, a and b. So d square phi by dx square is equal to minus omega square phi. This is a eigenvalue problem which we need to solve for real omega. Let phi 1 and phi 2 be the two eigenfunction corresponding to the eigenvalue omega 1 and omega 2 respectively. Furthermore, let's assume that omega 1 is not equal to omega 2. We know that the solution for this eigenvalue problem is in terms of cos and sine. The phi 1 can be expressed as a linear combination of cos omega 1 and sine omega 1. So same way the phi 2 also can be expressed in terms of cos omega 2 and sine omega 2. Let's keep this exact solution in the back burner and let's assume that we know nothing about them and continue in principle phi 1 and phi 2 are the two solutions corresponding to two eigenvalues omega 1 and omega 2 and see how their orthonormal properties work out. Okay, so phi 1 and omega 1 and one side we have phi 2 and omega 2. So the phi 1 satisfies the differential equation d square phi 1 by dx square is equal to minus omega 1 square phi 1. On the other side, phi 2 satisfies the condition that d square phi 2 by dx square is equal to minus omega 2 phi 2. Let's multiply first equation by phi 2 and the phi 2 differential equation with the phi 1. That means that phi 2 d2 phi 1 by dx square is equal to minus omega 1 square phi 1 into phi 2. On the other side we have phi 1 into d square phi 2 by dx square is equal to minus omega square phi 1 phi 2. Let's call this equation A and equation B and let's subtract equation B from A and then we get phi 2 into d2 phi 1 by dx square minus phi 1 into d2 phi 2 by dx square is equal to minus omega 1 square minus omega 2 square into phi 1 and phi 2. Let's play around with the this equation and let's bring in the phi 2 also inside the differential. It's just a simple algebra so that some terms get simplified because of this subtraction. So we bring in phi 2. Okay, this results in the equation d phi by dx of phi 2 into d phi 1 by dx. The extra term which comes because of that is subtracted is d phi 1 by dx into d phi 2 by dx. Same way on the other term becomes d by dx of phi 1 into d phi by d2 and the extra term which is comes out to be d phi 1 by dx into d phi 2 by dx. It is the same. That is why we do this simplification, resulting in an exact differential. On the other side, we do not have any change. We get the same equation. Let's remove the common terms. We don't want these common terms, and we end up in having a d by dx phi 2 into d by d phi 1 by dx minus d by dx phi 1 into d phi 2 by dx is equal to minus omega 1 square minus omega 2 square into phi 1 and phi 2. Okay, let's just rewrite that equation. Let's integrate both sides with respect to x and in the interval a and b. We get integral a to b d by dx into phi 2 into d phi 1 by dx minus integral a to b d by dx phi 1 into d phi 2 by dx into dx. This should have been dx equal to minus omega 1 square minus omega 2 square integral a to b phi 1 and phi 2. We recognize that this has a phi 1 dot phi 2 because it is a square integrable function, L2 function, and then this is an exact differential which can be simply integrated out, and which results in the equation that the phi 2 into d phi 1 by dx minus phi 1 into d phi 2 by dx evaluated at the boundary a and b equal to minus omega 1 square minus omega 2 square into phi 1 dot phi 2. So this is a dot product between the function phi 1 and phi 2. We have seen earlier in the case of matrices, eigenvector corresponding to distinct eigenvalues are orthonormal. In this case, however, we see that it is not zero. We get a term which we need to somehow get rid of. This term becomes the phi 1 dot and phi 2 dot becomes 0 for omega 1 not equal to omega 2 only if this term phi 2 into d phi 1 by dx minus phi 1 into d phi 2 by dx on the boundaries, that is at x is equal to a and x is equal to b, becomes 0. So this is the extra condition we have in the case of Hilbert space, which is does not come in the finite dimensional vector space. It should be eigenvalues. The eigenvector corresponding to distinct eigenvalues are orthonormal if and only if the term within the bracket vanishes on the boundary, that is x is equal to a and x is equal to b. Though it looks like it is a complex combination to go 0, but there are simple cases where it vanishes 0 because it comes as a product of function and its differential, or to be exactly, it's a Wronskian of phi 1 and phi 2. The simple cases for which these combinations become 0 on the boundaries can be divided into two parts. One is at which the functions phi 1 and phi 2 becomes 0 on the boundary, and that is called the Dirichlet boundary condition. And the other condition is that the derivative, that is a phi 1 prime and phi 2 primes on the both side x is equal to a and x is equal to b, both vanishes. The derivative vanishes on the boundary, and this condition is called the Newman boundary condition. If the eigenfunction satisfies the Newman boundary condition or Dirichlet boundary condition, then the eigenvectors corresponding to distinct eigenvalues becomes orthonormal. Okay, now let us look at the solutions for our simple differential operator d square by dx square and their eigenfunction, how exactly they satisfy these boundary condition leading to orthonormality. We take our region from minus pi to plus pi and see on the boundary, that is at minus pi and plus pi, whether it satisfies one of these boundary condition to give orthonormal eigenfunctions. The function sin x vanishes at minus pi, and it also vanishes at plus phi. So it does satisfy the Dirichlet boundary condition. On the other hand, function cos x, whose derivative, which becomes sin x, is exactly vanishes at minus pi and plus phi. Both functions, eigenfunctions, sine and cos, do satisfy one of them, and we can have them as a eigenfunction corresponding to different values of omega. Of course, if this has to satisfy, the omega have to be integer, otherwise n pi x would not be 0 for n not equal to integer. Omega is not integer, omega x would not be 0 for minus pi and plus phi. If we look at that, it also satisfies this condition in the interval x is equal to 0 and x is equal to pi, and this also gives us a freedom to work in the interval minus pi to 0. So these are the interval in which we can apply these two boundary condition and use sine and cos as a orthogonal function to express any function. So we see that the sin x satisfies the Dirichlet boundary condition at the boundary minus pi and pi. On the other hand, cos satisfies the Newman boundary condition at minus pi and plus pi. We also have seen that the 0 also can be included. Either we can use 0 to pi or minus pi to pi to satisfy the same condition. We have one more interval in which this can also be used as orthogonal functions, where boundary condition Dirichlet and Newman boundary conditions are satisfied, that is between minus pi by 2 and plus pi by 2. In this case, cos satisfies the Dirichlet boundary condition and the sine satisfies the Newman boundary conditions, and that is where these functions become orthonormal for integer frequencies, that is omega equal to n, for n is equal to 1 to infinity. So we can use them as an orthonormal function. The eigenfunction sine and cos of a differential operator d squared by dx squared from the complete set for omega equal to 1, 2, 3 and so on in the interval between minus pi and plus pi. We also have another interval. Let's keep that in the back of our mind. It is useful when we use it for different practical purposes. A linear combination of function of sin nx and cos nx can span L2 function in the interval minus pi and pi. So this representation of a function in terms of sin and cos is called Fourier representation or Fourier series. So we have sin mx and cos mx are orthonormal to each other, and sin mx and sin mx themselves are orthonormal. Same way, we have a cos mx and cos nx are also orthonormal to each other. With these orthonormality condition, we can completely define Fourier series. So let f of x be L2 function in the interval minus pi to plus pi. It can be expressed as f of x is equal to some I is equal to 0 to infinity a n cos nx and plus I is equal to 1 to infinity bn sin nx. Note that I is equal to 0 is included here to include the constant. Some people simply use this also I is equal to 1 and simply add a constant here. So depending on whether you want to include the constant or not, it is just a convention. Here I have to keep the series symmetric and neat, we could put included only sine and cos term and not constant. Constant is absorbed in the cos series by taking I is equal to 0. Of course, when a vector is expressed in terms of basis, the coefficient are determined by taking the dot product with the basis element. With that, the coefficient a n becomes f of x, taken a dot product with the cos nx, and then we get that as 1 by pi integral minus pi to plus pi cos x into cos nx. This pi comes for a normalizing, otherwise your function will not be orthonormal. So your a n, if you put cos nx, it need to be delta mn. So that is why this normalization is used. Similarly, the of course for n greater than or equal to 0, and n is equal to 0 corresponding to the constant or the mean of the function in the interval. The same way we can define Bn, that is f of x taken dot product with the sin nx, and in terms of integral it is expressed as 1 by pi into my integral minus pi to plus pi f of x sin nx dx for n greater than or equal to 1. This defines the Fourier series, and we'll apply it for the some of the interesting cases and see some of the properties of Fourier series. It's a very important tool both in theoretical and applied physics. Then we'll go on to Fourier integral and also study their property. Let's stop it now here.